Right, so we are going to look at the solutions of task number 2 of the week number 76. So yeah, welcome everyone, and the task is called word search. So let's look at what this is about. So there's some grid, basically the grid of letters. Write a script that takes two file names. The first file would contain word search grid as shown below, like this one. The second file contains a list of words, one word per line. You could even use local dictionary file. Print out a list of all words seen on the grid, looking both, basically in all directions. That's clear. Output found 54 words, blah blah blah, and here are the words. Okay, so this is clear. So you've got some letters, you've got a dictionary, an English dictionary, and you have to find all the words which you can find here in all directions. Right, so let's look at the solutions. This task is a bit more difficult than others. So for example, I have just to test those, I have this dictionary of almost 90 English words, low-cased, and there are no plural, just dictionary forms. And I will be using this depending on the situation. Okay, so let's start with these solutions. The first solution is Arne in the list. The first solution in the list is Arne's solution. Let's look at this solution. So what we have here, so here we take the dictionary, basically the path to the file with some default value, the path to the file with the grid, minimum lengths of the words to find, right? Minimum words. So how many words are there with one letter? Well, there are a few, I believe. Right, so then we read the grid. How do we do that? We do that. So actually, in Raku, this is really it is extremely easy to open a file, read the lines. So basically, the selected thing is what you need. So you have the file, the path to the file in a variable, in a string variable. Then you create the IO path class, and you just call the lines method on it, and you just get for free all those lines in the file. Okay, so then we map them and we convert them to lowercase and split to words. Not quite clear what that means because grid. Okay, so probably we have to look at the grid in this solution. So let's cut Arne Raku grid. So this is a grid. So so there are some things. So basically if you split with words, you basically get the letters. And then you get the lists of these letters, right? Okay, so this one is really also another really interesting concept. So basically here, with just a few characters, we check if all those lists have the same lengths. So if basically the grid is correct, there are no short or long lines in it. So you see there's a reduction operator, and basically we convert the array of lists, the array of letters, the array of lists, right? So in each, there are some, each element corresponds to the original line in the file grid.txt. So we just convert this to the number of elements, basically the widths of the string, and then we compare all the strings with the reduction operator. Probably we can use something, actually no, we just basically insert this equals between all those lengths, and if one fails, we fail. And the same, this similar construction for, what is it? So single character only in grid, because we have these words splitting, and if at any position there's at least two letters, we also should fail because this will not be passed if I'm correct, right? So dot cars maximum, right? So if maximum of maximum, basically, so you scan horizontally and vertically, and if the maximum length is bigger than 1, what happens if there's 0? If it's 0, then we will fail this check. Okay, so then get dictionary. Let's look at the where is it? Get dictionary. It's here, and okay, so actually it's a separate subroutine, but actually this subroutine only contains a single line, again a similar line. So we create the IO path class, call lines method, get all lines, and then just grab all the lines which contain non-word characters, right? and then make it lowercase, and then create the set out of that. So yeah, basically we just exclude repeating words. Actually, my dictionary does not, well, should not, I don't know if that's correct, contain repeated words, but that's not that. Okay, so dictionary is the map. Actually, I see. So you return the set, and is this set applied? So basically, is it what is called for every of these, or is it called in the end? It's not quite actually clear. Right, so nevertheless, so this is the dictionary. The candidates, probably the words that we are going to print here, like append, return candidates. So rows, number of rows, number of columns. Yeah, actually, this is also the pattern that we use quite often. I wonder if there's a simple way just to, if you have a square or rectangular matrix, how do you determine its height, right? So you need to take the one of the rows, which one, the first, the last, whatever. But if it's like really a square or rectangular, so there should be a similar method. But nevertheless, so okay, so we start. Yeah, basically we go through all the cells, right? We print this, and we collect the candidates. So currently we are at the position at some letter, right, somewhere in the middle of the matrix, and we try to get candidates from that position, try to find them. And after that, as soon as we found the candidates, we create words again. So yeah, so we want to make sure that the words are unique, because yeah, there might be similar words found in different places, and we then sort them. Just probably we can sort it in the end, right? Because then we still make some grabs, and why bothering like us with sorting the bigger list if there should be a smaller list outside? So I think I would move this sort to the end. Right, then we sort, then we grab, then we filter out the words which are too short for us, and just before that we only grab the words which are in the dictionary, so for which this dictionary exists, right, this dictionary entry. Then found number of words again, so look at how easy it is to print the length of the array just inside the string, so just interpolation. And the second even better thing, where you can just interpolate the comma separated list inside the string, so you don't have to create any separate variable, you don't have to concatenate strings, just put a pair of braces, and that's it. Okay, so get candidates, the most interesting probably function in this program. I mean, in the whole algorithm, not necessarily this program. So there are some candidates. There is some comma, so we are going to create more than one thing. So we just put this as a single entry, like as a scalar into the candidates array. And so these are basically the directions, right? So for left, right, up, down. Yeah, 0, 0 should be skipped, because this is like a non-move, right? This is where we skip this. It's the central position, the current letter. And from that position, so we do get candidates. So it's just get candidates, and this is like really getting candidates at that position for that direction, right? That direction, and right. So we just here determine the direction. And we do not find any words here at this position, but we believe that this do get candidates function will give us something. Okay, so that's the current position. That's right. My candidates loop row. So we increment. Okay, so these are basically the increments, the direction. So it's always either plus or minus 1 or 0, but not both 0. And we just in the loop we just try to increment while we can. Last, so if we reach the border of the matrix, then we stop, and we just append these words. So basically, we don't know yet if this is word. We just take all the words from this current position in the given direction, and there will be a few words like of increment in length. Actually, yeah, and we just push the candidates and return the candidates, and after that, basically, we for each position, for each letter in the original grid, we will have, like for example, if we are here, so this array will contain this D, DD, DDL, DDLA, and so on. and then again upside, downwards, right, and I cannot select it by diagonal. So yeah, all those just huge amount of words which we just have to filter. But those will be all the possible words in this matrix. Right. Yeah, probably there will be some duplicates. For example, if you go up and down from different positions, or for example, if you from this letter L you go downwards like this, and then you go from this R upwards, you will have the same word again, but no, it will be a flipped word, right? So they will be different. Okay, right. So the only thing I want to comment is probably there's a chance to use something like this, right? This form of reduction operator with the triangle, well, basically triangle reduction operator, because this is exactly what we want. So we have some letters in the given direction. So these are the letters in the given direction, vertically, horizontally, or diagonally. And yeah, it will give us a list of strings with incrementing lengths, right? Probably it will be a bit simpler than this, but nevertheless, so this is quite clear how the program works. Let's run this. So to run the program, we have to run Raku, Arne, Raku, Ch2, and what do we need? So we need the minimum lengths, for example, like 4 or 5 letters, and the dict I saved here, Raku reviews 76 dict. And the grid, the grid is the Arne Raku grid, right? Yeah, so it takes some time. And it found 33 words of length 5 or more. Social, yeah, squash, depart, enter, right. So yeah, theorem. Okay, yeah, there are some words that appear in this dictionary. Okay, so yeah, that's good, and I think it's simple enough. It's quite clear what this program is doing. And yeah, probably should just remember this pattern. Well, not necessarily like letter by letter, but just the idea of how you can make a simple check with just a few characters. And of course, this one is a very useful thing, and I believe we will see it in other solutions too. And maybe before we go, so we see the where clause checks if this is a file. So if there is a file, so directly in this main condition, in the main function, we can check the condition if this path is a file, right? And .r. Okay. What is .r? If it can be open for reading, right? Okay. Well, yeah, maybe. Docs Raku. So this is IO returns you this thing, the object of this class, and there are some methods, and method R returns true is a path that exists and is accessible. Okay, points to the non-existent file system. And F, where is the F? Is a path exists and is a file. So yeah, we have to check. I wonder if do we really need both for this simple task, but nevertheless. Okay, so let's go next. Jan Kranavik, okay, no solution. Yeah, Jason Messer. Right, here it is. Okay, well, yeah, this is big, but actually, if you see, there's a set of similar subroutines for different directions, like north, west, north, northeast, east, and so on. So yeah, basically, we have to understand how one of them works. But again, this is just the thing for different directions. Right, so we take the dict. The dict is probably the path, right? Where is the dict used? Right, so here it is. Okay, so we open it. I think it's a bit like redundant. We can just use io.lines button. Okay, so we fill this with we fill the dictionary hash with those words. The key is the word, the value is true. Yeah, again, we can use a set here in this case, as in the previous solution. Okay, so we read the grid, and we do that by reading lines. And what do we do with those lines? Okay, so we have these lines, and we comb. So I believe this grid is a bit different, right? So if we look at the cat JSON Raku grid. Yeah, so it does not contain any spaces, so we can comb the lines instead of splitting it into words, and we convert it to lowercase. Then so the dictionary. Okay, then for from 0 to the last grid element, which is the x is here is what is it? This is the vertical coordinates, right? No, actually this is horizontal coordinates, but it doesn't matter because if it's square, but actually no, it is so y. I think this is y, this is x, right? But okay, yeah, it's not that important. And so we start this position and we go to different directions. So directions are determined not by indices which we pass to the function, but just by the function. So I believe we can just pass the, yeah, probably the most important difference in those is this check, right, in these actions and checks in the loop, right? So yeah. Okay, so yeah, yeah. Then we grab those probably words which are longer than 3 characters and save if .elms bigger than 0. So I believe we're using dictionary somewhere or not. Right, we do use the dictionary. So okay, so let's look at this. So potential is the thing we going to collect the candidates into, and the found is what we return, right? So this is even not needed because it will be returned. It's not used, right? The variable. So gather. So in the loop we're gathering and we're taking something if it is in the dictionary. That's clear. So all those are already in the dictionary, right? And if we can grab them with those 4 lengths or longer words, we can print them. Otherwise we just skip the whole row. Yeah, by the way, so we see, so there's a for loop, there's another nested for loop, and there's like a set of with calls. With you topicalize the current thing, right? Which is the current thing here. Okay, then you append the thing in lowercase, but it's already lowercase, isn't it? We already have it, made it lowercase here. So yeah, so basically we just in this direction. So I wonder how do we okay, so yeah, in this loop we increment the x or y depending on the direction. So for example here this is -1, so we have to decrement both coordinates, and here it's -1, so we go in left and we only decrement the x coordinate, y coordinate stays the same. Okay, yeah, that's also very clear. Probably this can be optimized a bit, but even we can use multi functions and just pass those -1s. So I mean, even if we still keep that many functions, we can create that many multifunctions and pass those -1 and 1 instead of the name, right? So just add this 1 and -1, or just use the string like this, and w as the third parameter, which will be a string. And okay, yeah, but why not? Okay, so let's run this program, and to run this we need to pass the dictionary and the grid. We need also a grid, so probably this is the JSON Raku. This is what we have to do. So we have to call Raku chat2. The dictionary will be taken here, and my dictionary is this one. So we're expecting to find 4 letter words. I don't know what this means. So, well, I mean, I know what this means. So these are the words that have the similar part in the beginning of the word, right? Right. Okay. So yeah, that's USSR. Okay. And yeah, next word is rape. Oh my god, just read this. Okay. So let's go next. Luca Ferrari. Probably you want to read some textual information before going there. And let's look at the solution. So here it starts. So we need the grid. So okay, so we have to Luca Raku, go there. So there's this grid. Let's look at this. So it's with spaces, and then we need the okay, so yeah, then we need some words and the minimum length. So information. Okay, so we start with reading the lines from the grid. We split them by spaces, skip empty, array, then horizontal, verticals, diagonals, grid characters, horizontal, push, oops, wow, join, flip. So grid characters. So I believe these are dot join, and flip. So this horizontal basically gives us, will contain the list of like dot join. It's just the whole horizontal line, and this one is the whole horizontal line but in different direction, right? So I believe we are not going to scan the matrix in different directions, but instead we just immediately, that's wise. So verticals, so basically yeah, that I like this. Then diagonals. For diagonals, definitely it's a bit more difficult because there are 4 different directions here. Yeah, see, so so this is how you go vertical, right? Interesting. That's really wise again. I mean this spot. So instead of just manipulating indices, you can do this, and maybe I want to run this program, but I'm afraid that there will be too many in the output. Too many characters in output. Right, then you go diagonal words, so you're going to probably do similar thing from the source grid in different directions, right? So let's look at this grid, diagonal words. Diagonal words, so up, down, left, right. So right, so this is where we prepare some things that we're gonna use later, because the algorithm itself does not depend on direction, right? Just different deltas. While the last row grid, right? So what we do? We set the column. So this is where we right. So this is where we collect the letters for the word in this given direction. So here all this is required to just make a step to a neighboring character in one, basically to the neighboring character in the given direction. The direction is given by the combination of these 2 Boolean variables. Then we collect the words, and again we just immediately make the flip. So the only thing I don't quite yet understand is how do we do. So we collect this, right? And we do this for all the dimensions, and probably, right, it's like all diagonal, right? It's regardless the position, so there will be like matrix which goes 45 degrees through all the letters. Then last column. Okay, so I kind of then we skip single letters, right? So the word I will not be found, and that's it. So that's wise, right? So we prepared basically all the lines, all the possible lines, both from left to right, from right to left, up to down, down to right, down to up, and all diagonal potential words, right? So the longest word will be the number of elements in the longest diagonal right here, and the shortest word will be 2 characters, because yeah, we skip all the short, all one. Basically, we skip the corners, right? Yeah, basically we skip the corners. So this T and this D are skipped. Maybe L is also, and B is also skipped, but this LI and IL will be the 2 words in the diagonals array. So, and actually we just Actually, we probably don't need these three horizontals, verticals, and diagonals, three different arrays. We can just put all the words into candidates, or not the candidates, but just into like lines, because we are going to check them exactly in the same manner. So all those the same way. So we use these diagonals for 4 different directions. So we can just put all those verticals and horizontal lines into the same array, right? And we can eliminate this check and replace it with a single check. Right, then what we are going to do, so how do we determine the words? So for all the words, word file name, so in a dictionary, we skip if there's an empty line there, convert lowercase, found words, push if current word in, if push the current word if we can basically find this. Okay, so yeah, just a simple basically index of like we just try to find this word in this sequence, in this line. So we're testing all the words from the dictionary. Okay, so that's kind of the complexity of the algorithm is proportional to the number of the words in the dictionary rather than to the number of potential words in the grid, right? So this is the opposite. Probably that's not that good, but for like 1000 words that should just work. Okay, so where we are here, and we can run this chat2. What do we need there? I forgot already. So we need the grid. Okay, grid is here. Then we need the dictionary, and we need like 4 as the lengths. Searching words from this file into grid. So here we are currently scanning all the words, if I'm correct, right? All the words in my dictionary. So maybe let's open this dictionary and remove like everything here. It should be faster, right? No. Right, but something is found. Okay. Yeah, and this is obviously from the dictionary. Okay, so yeah, so maybe before we go, let's just copy this program and make some examination of what it actually does. What I want. So okay, so I will. Diagonals. So this is different diagonals, right? So my lines of strings, right? So basically these are the things. This is where we can do it like this, and this one we do it like this, remove all the rest. Okay, let's have a space here. Just let's remove this one. And here we also need some strings, and that's it, right? So but what I wanted to do, not just to replace this, but I just wanted to say these strings. Again, my keyboard is printing double R. Right, let's oh, it's still searching, so I believe, yeah, we can just stop here. Okay, so Raku T. Oh my god, we need the grid. So this is the grid, right? Cut grid txt. Here is the grid, and so it's Raku T grid. Then I need the dictionary and the lengths. Probably let's even do it like this. String is not declared. Where is it? Here, right? Okay, so these are the words that we found in the actually not that simple, because okay, nevertheless, so yeah, probably this should be done a bit differently, but you got the idea, I believe. So but you see, so this is the first line, and then you will find some blue, where is it? Yeah, here. This is the vertical column from this crossword, and those two Actually, there should be 4, right? These 2 and this 1, 2, right? There are 4 are the diagonals. So the only thing you have to do is just to flatten this array. Okay, but it's still searching, right? Because we are scanning all those 90,000 lines. Okay, yeah, nice. But the idea is really good here. Probably after that, instead of scanning the lines, we can just again create different, using the triangle reduction operator, different words from the given lines, from the given strings, vertical, diagonal, or horizontal, and then just take a look at the dictionary. Okay, going next, Mark Anderson gave us this solution. So here's the example of the output. So we need the grid and word list, and the program why word list doesn't include plurals. Okay, so we are going to use the lingua inflect English from Perl 5 for the plural. What does it is? I believe it's not Polish, right? So the grid, the word list, and the lengths, array of arrays, grid lines, map split by space. So again, array and array, then the strings from this array of the words. So this is probably where we take the grid and take all and try to find all the words, the potential, the word candidates. Return an array of string which consists of the horizontal, vertical, and diagonal of array of array. It also includes the reverse of each, right? So again, so just instead of scanning it in both directions, you can just call the flip, like here, and append it. Yeah, so this is just giving you half of the work. Right, so there's so we zip them. Okay, reverse. Well, yeah, so string push. Okay, so here are like I wonder why we have reverse here and flip here. So these strings should contain all of them, right? But nevertheless, so this is again we go through all the potential directions, horizontal, vertical lines, and all the 4 diagonals. Then we skip the words which are short, then we make them unique, which is good again. And yeah, so and this array already contains all the possible words that you can find in the given grid. And after that, just gather, so words is the result, and again we filter it, so we flatten it to make it unique. So we are gathering the words, so take, so the word is taken F, so we skip just the first word list, so we skip the word in the dictionary if it's short enough, that's wise. And for all the words in the string, so for all the word candidates, so this is the word candidate, if the string contains the uppercase. Okay, so this play with upper and lowercase is a bit annoying. I mean, so and then if the word is bigger, the given length we're taking is in. Okay, so that's like we are making the plural form of the words, because yeah, the dictionary assumes that. Okay, so that's probably the thing to be defined in the definition of the description of the task, whether we want plurals or not. But yeah, here we just force plurals to be found if they exist, and we do the same. Okay, and then we just print this. Okay, so we can run this program. I wonder, probably no, we cannot run because I need to install this module, but I believe that this is the output that we will get. And again, so we are searching. So here in this program, we find the word candidates. There's limited amount of them. They may be a big list, but still it's much, it should be much shorter. By the way, we can, maybe we can actually do that. We can go to the first solution that we saw today. So it was Mark Anderson. Let me put a mark here so that I don't forget. And I will go back to Arne's solution. I will copy this solution and I will print the number of word candidates so that we just understand what's the the order of this. So this is the candidates, and return candidates do get candidates. This is the words, right? This is the words here. So here we can say candidates.elements, and we don't need everything else, but I cannot remove it. So let's so Raku T. So okay, so we need the minimum, say like again 4 characters. We need the dictionary. Where is my dictionary? And we need the grid. It's a space separated grid, which is good. M equals 4. Right. Single characters only in grid. So what's the... They are in the grid. Grid. Yeah. What do you mean, single characters? Single characters in the grid. Single characters in the grid. Let's just take cat Arne. Cat Arne grid. Raku grid. So this is, but it's the same, right? So cat grid. What? Why? Single characters only in the grid. This is a good grid. Yes, it is. So this is our grid. I don't understand that. So it stopped working. So the first is the dictionary. The second argument is the grid itself. Right, this is the dictionary. This is the grid. Ah, okay, so it's dictionary. Oh my god, so I spent so... It's grid. Right. Okay, so now I want to see the number of... So there are less than 17,000 candidates, which is like, yeah, like 5 times less than the number of words. Okay, that's good. So, okay, so the next will be... So we were at Mark Anderson, and the next is Markus Holzer. Here is his solution. Right, so here is the solution. So let's see what's there inside. So the function, the main function takes 2 parameters. So it's the dictionary file and the board. And let's look at the board, what's there inside. So it's the file with spaces inside, okay. And by the way, Markus also commented that there's this file explained. There are some explanations, and actually it also prints the thing, so we can run this file, and also we'll return to this file to see the explanation to this function. But well, let's enjoy this the compactness of this solution first. So words, basically it's just the dictionary for based on the given file. Characters, it's a bit different from what we saw before in other solutions, but what we have here, so we slurp, so we basically we read the whole file, then we comb it, we split it into pieces using this regular expression. Well, there are no regular expressions in Raku, there are regexes or regexes, whatever you read it. And so basically we split it by not, so capital letter means always kind of not H, not horizontal space, right? So basically a vertical space or whatever, or anything else, right? Then widths, so we try to find the index of the first new line, and that's the widths. Okay, where are we using it? We're using it here. So basically, so this one is a linear array, right? If I'm correct. So that's why we need to compute something based on this width. Right. Okay, so then we have this, basically the main body of the function of the program, and so what we have here is the call of words in. Basically this is the function, and you see, so, and this is the function call. There are no parentheses, but you should just immediately see that this is the function call. Then we have these rotated chars, and this is actually another function that returns something to which we can apply this flat and join. So we flatten the result of that function call. And then for all those things, we just basically print them, right? Yes. Okay, so let's look at the functions. So the first function is words in text, and we build a text string out of the text and the flipped version of the text, separated by a new line, and then we apply a regular expression. Well, yeah, let me call it regular expression. So it's M for match, I for ignoring the case, and X is for exhaustive search. All right, let's just, there's really good search on this website, but not always. Exhaustive to find all possible matches, including overlapping ones and several ones that start at the same position. Alright, so basically we will find everything that we can find there with this. And also you see, so the array is used inside this regex. This is really cool thing. I have an example here. I tried it just before. So for example, we have this words array with 3 words, alphabet and gamma, and we match the string beta against this array. So we do nothing, like we don't have to join this, we don't have to organize a loop, just pass the array and you get the result that you expect. Right, so we could find the match. Right, so okay, so next, so words in, so we will find the words in some text, right, the text, and this text is actually this thing, right? So it's rotated characters. Yeah, don't be confused, there are 2 functions with similar names, just like ed is the only difference in the name. So first we call this function, right, rotated characters. So characters, we've got these characters from, you see, it's a one-dimensional array. Then we split it into batch. We saw this batch method somewhere earlier today by chunks of widths. Then there are 3 different directions, and actually maybe now I can switch to that file with explanations. So just so the output is in the right order, so we apply this eager. It was not there, right? So basically we consume the result as soon as we have this result. Then horizontal lines, right? Basically. So this explanation really explains the thing. So if we split it into chunks of widths, then basically those are the horizontal lines. And so this thing, right, which is mapped. So these are basically the directions, vertical line. Then, so these parentheses are around directions, right? Left, right diagonal, right, left diagonal. Then we map them using these rotate characters. Rotate characters. So we take the offsets. These are the offsets, I believe, right? And again, eager up to width. From 0 to widths, we map those and we apply this pointer block with the parameter start. So the first and the next indices are computed based, as I said a bit earlier, based on these widths and some other things, so basically offsets. And and we just return those characters, right? But this is also a really interesting thing. So we define the first and the next character, the first 2 characters, and then we just use the sequence separator, and Raku does the job. That's cool. That's really cool. Okay, return back. So here is the solution with no explanations, but it's a bit optimized. There are no additional variables there, but the result is really impressive. So you start somewhere, right? Then you compute the offset comparing from the current position based on the known widths and on the given offset, right? So the different direction, and then just 3 dots star and yeah, whatever. It's all computed. Okay, so it's time to run the function. The program, Raku Markus Holzer Raku Ch2. So okay, Raku. So we need two files. The dictionary. Where is my dictionary? It's here. Then we need to pass the board, which is again dictionary. So this is a grid. There's no grid here, like here, right? And that's it. So, and it should final. And by the way, there's no limitation for as to how long the words should be, right? To appear in the result. Wait, there's no result. Okay, maybe my dictionary is huge, and maybe let's explain. Let's run the second file. Right. So yeah, it's too quick. Okay, so it prints the dictionary, which is probably a bit too much, because they were like, you remember, 90,000 words. Then there's the grid. Then okay, so right, searching these characters. Those are the characters from the grid, and you see there are new lines. And you remember that where was it? We used these new lines to compute the widths. Grid has the width of 17. Rotate the grid with offset. So where does it happen? Explained. Rotate the grid. So yeah, this is the function which was called here after you've got the directions. So this is the direction, horizontal or vertical line, and two diagonals. And you see, so there are indices. So this is basically okay. Maybe let's see this example. So we create basically the indices. So we compute the first two of the sequence, and basically all the rest is just plus 17, plus 17, plus 17. For diagonals, it's plus 18, plus 18, plus 18. Indeed. So yeah, basically, it's so simple. So basically, to compute the diagonal, you just need to increment by the width plus 1, right? And for this, it's yeah, you start with 1 instead of 0 here and there, and you increment it by the width minus 1, 16, 16, 16, and so on. That's a really nice observation. Okay, then data after rotation. So after rotation, where is it? So data after rotation. So right after we call this rotated characters function, these are the data, and I believe those are the horizontal, vertical lines and all diagonals, right? So there are some. Then final text to search. So this is the text, right? And yeah, those lines are separated by a new line character, and you see, so there are long lines which are obviously the horizontal and vertical lines, and there are some short lines like this one, which is obviously the diagonal somewhere close to the corner. And finally there's a result, and I press Ctrl C, but I believe I just used to do we have a dictionary here in this repository? I wonder if you can just use this one. So we have words, words small, right? There's another, by the way, there's small board, right? Just a bug. Yeah, maybe let's do it like this. Let's submit the small dictionary, Markus Holzer Raku Ch2 words, Ch2 words. Hey, what's up? Right, so here are the words, they're capital, by the way. So, and so I wonder how many words did we find. So we found 40 words, and there were, you saw that there were like 54, if I'm correct, words in the dictionary. So yeah, it's not just printing dictionary, it really finds theorems, constitutions. Yeah, really nice. Okay, good. Great. And before we go to the next solution, we have to look at this golfed. Probably we should start the golf contents indeed. So this is the golf version, and yeah, see, so yeah, you can gain a few characters on just removing spaces, but you should really test those things, because you cannot omit every space. Well, definitely after keywords, but I believe there are some cases where you have to have these spaces. But nevertheless, this is really really cool for golf, and probably for golf you have to do something with that. I don't know what, but yeah, for example, if you will use angle brackets, you will not save any characters because you have to replace a comma with the space, and yeah, EX, it's already golfed, exhaustive. Long word can be used there, but yeah. Yeah. Okay. Slurp, subst. I see. So this one is using different thing. Okay. Let's not spend time on this. This is really cool, but not for our discussion today. Okay. So I'm returning back to the next solution. So it was Markus Holzer, and the next solution, where it is, wow, probably I should go okay. So the next solution is a solution by Shahed Nooshmand, Raku number 2, and what we have here is, oh yeah, also a short solution with, I already see the thing that I want to show you. So okay, so we take the, well, 2 file paths, then found words, we read this. Yeah, see, so it's even probably more straightforward way of reading the file, right? It's just called slurp and pass the, really? I didn't know about that actually. Slurp, yo. Sub, yeah, indeed, so you can just directly pass the file name, right? That's cool. So use this practice, and probably I will even have to write it down because I really want to use it. Okay, so you slurp this, then FC lines. What is FC? Actually, there are so many things in Raku that I even sometimes I didn't see it in default case. Yeah, this is what I thought. All right, it's like LC UC, right? So I use this thing. Okay, yeah, the thing you see, so the gross and gross with double S is because, yeah, this SZ is double S. Right, then grid, so this is the grid. You do more or less the same, but you convert those to words, those lines to words. Rows, this is the grid mapped to the joined versions, right? And also cached. Just read the documentation about this cache. It's really a thing. And also there's the experimental thing that with isCache or isCached that you can apply to the function and get these function results like memwise. Okay, so there are some columns, so we cross zip those grids and again join those results, right? Diagonals 4, so there are 4. Where is it 4? Yeah, I believe this is like 2 diagonals, so it's rows, these are columns, so these are the characters horizontal and vertical, and these are diagonals 1, 2, probably different directions, right? Or maybe not. Yeah, there's flip here, so we don't need, actually there's reverse here. So then for the width, right, so we took the two-dimensional matrix and we took the first thing and we just took the size of this diagonals. So yeah, we collect characters, right? We collect and then we also concatenate the results into a single string. So we take something. Basically, we subscript the current topic item if we can actually, if it exists, right? Otherwise, if this one is undefined, we just break the loop. And yeah, so this is what we topicalize. Basically, we topicalize this grid and we subscript this, and also we increment the index at the same time. Okay, I can't say that I quite understand, but I understand that basically here in this loop we fill the diagonal strings and also we make them reversed, right? Okay, but after that, so we've got these words. Ooh, this is dictionary, so I wonder if again I should use the small dictionary. For each word in a dictionary, we add this word to the found result if, but that one is cool. So you see, so there are vertical bars, which is kind of a junction, if I'm correct, right? So if one of those can be grabbed and it will contain either a word or a flipped word. All right, so we so this reverse is not actually, so yeah, so we, yeah, in previous solutions we were flipping. In some of the solutions they flipped the grid, right, the lines in the grid, but here we can flip the word. Well, actually, yeah, why not? That's a good observation as well. But the interesting thing is how this vertical bar for junction is used here, right? That's cool. That's amazing. Well, with the only exception that probably we don't need three again. We don't need three different arrays. We can just collect everything to a single array and make it unique, and then grab. The thing I don't like is probably this will be a bit slow for big dictionary, because what we have to do for, so basically we have to scan all the dictionary words and we have to try to find our lines in those words, right? Our words in those lines, but yeah, okay, but you got it. And then we just print result. Okay, nevertheless, let's run this solution. So Raku, maybe even you see, maybe we can just do it like this trick. Shahed Raku 2. I hope it's Raku. Yes, it is. Then we give the grid. Then we give the. So here is the grid. I believe there's the grid for this file, right? No. So then, yeah, okay. Then basically this, and then the dictionary. So I'll submit this small dictionary of 54 words. Yeah, and everything else is found. And yeah, how many? 54. Basically, this is the whole dictionary. Okay, so let's just give us Raku review 76 dictionary. It's a big dictionary, so it will be really slow, and it is really slow. Maybe we can just change the code, and you see the computer is slow now. So maybe we can just do it like this, and instead of this, well, print. Wow, why did I use print? Right, so just print immediately as soon as we found the word. So probably at least we will see the result. So Raku T, and what we need the dictionary and the grid. And our grid is the one we want. Okay, Raku T dict grid. Too many arguments in flattening array only. Wow, that's okay. That's the thing for flattening array only. Why? It's 21st century. Okay, nevertheless, let's make this array like what we want. Okay, let's just split it into two pieces, not equal pieces. Right, but still, yeah, definitely it's slow because we have to scan the dictionary, which is still big. Okay, let's stop this because my computer becomes really slow. Okay, going next. So it was Shahed, and then the next is Proctor, Raku number 2. Here is the solution. Okay, we start. So subset valid file is a string for which the exists the file name, right, with this name, the file with this file name. Okay, so we take two valid file names, grid and dictionary, and the minimum word length. Horizontal lines. So we create the horizontal lines by just reading the grid. So I wonder, we're reading the grid a few times, or we're reusing the horizontal. So we are reusing the horizontal lines. That's cool. So horizontal line, yeah, basically this is just splitting by space and taking the result. Vertical lines is vertical lines. There's a function to call. Okay, so vertical lines. So we have these horizontal lines, and we determine the dimension of the rectangle, and after that we just scan this and we put this thing by different indices, swaps indices. Right, then diagonal lines and reverse diagonal lines. Okay, so let's look at the diagonal lines. Is really cool and simple because it's just diagonal lines across, diagonal lines down. And right, so there are two functions, but basically the idea is the same. So we just do some tricks with incrementing the indices in the correct direction and collect the thing. Right. Okay, so we've got all those rows. Then all matches. So it's horizontal line, reverse horizontal lines, vertical lines, reverse vertical lines, all diagonal lines, and all their reversed versions. So this is what basically every solution should has that uses these. So we can just put everything in a single array because we don't matter the actual position and location and direction of the word in the original grid. So then codes. Codes is kind of the length of the Unicode string, right? So this is the maximum. What is it? This is the maximum length of these lines, right? So basically it will be the diagonal thing. Probably you can compute it immediately if I'm correct. Definitely I'm correct here because these are just the lines, and this is their maximum lengths. Any match. Okay, so we're preparing this any junction, any dash junction, and there's another cool construction of Raku, the what's the name? It's the name, the feed operator, right? So we to get those results, which we are going to print a bit later, we are going to lazily read the dictionary lines, and you see. So again we are reading the dictionary first rather than creating a dictionary hash. But okay, so there's race, so we can so there are two functions, two methods, race and hyper, which are kind of opposite. Race allows us to make this computation parallel, and we don't have to care about the order. Then we grab those words which are not longer than the longest line and not shorter than the required lengths, minimum lengths. Then we map that to an array of two items, basically the word and the uppercase regex. Okay, then we grab those using this anonymous function, the pointer block, with the I don't quite understand the syntax here actually. So there's the pointing block, right? Really? So probably I should explore my thing, my knowledge about this, I don't quite understand. So is it like you're saying that this is the array of two elements? Okay, so yeah, this your homework, and actually my homework as well, and which actually return you true or false, depending on whether this match word is in any match. And any match, remember, this is the junction, which includes actually all the lines, right? So we take the word, the match, and we apply it against this all things that we know in the grid, from the grid. After that, so yeah, that's a long story to read. After that, again, you use this construction, and you it's kind of transformation, the well-known transformation pill, right? Right. Okay. So yeah, I think we looked at every piece of this program. So it's time to run this program. So it's Simon Proctor, Raku, big Raku, here, Raku, Simon Proctor, Raku, chat 2. And what do we need? We need two dictionaries. The first is the grid. So do we have the grid here? And actually, what does it? Main grid, small words. The grid, small words, and the small grid. Okay, so we need to pass this main grid. Simon Proctor, Raku, main grid, and the dictionary. Okay, so I'm brave enough to pass the whole dictionary, but I'm sure. So okay, so this is the grid. Right, so probably want to make the dictionary small enough. Again, maybe we can just use the one from Markus Holzer solution. Right, so here are the words, right, that we found in Constitution and Constitutions. Right, I wonder if it's there, right? Where is it? Yeah, so both are them. So remember there was a solution which uses module to just create the plural form of the word. Okay, going next is the solution by Athanasius, or Raku number 2. Okay, so here's the description. Here's the block that prints the message before the main program starts. Then we have the main function, which takes the grid. And again, we immediately want to make sure that this file exists, the grid and the dictionary and the minimum lengths. Then grid lines. So we read the grid and we make some simple string replacement, remove the spaces, right, from the lines. Then the search lines. Okay, so this is what I like. So basically we just again create a single array for everything. For the horizontal lines, here it's the trivial case. For the vertical lines, it's probably less trivial case, but there's a special function. Then diagonal up and diagonal down, across and down lines. And okay, so let's get vertical lines. Right, this is a function that is called here, and get vertical lines. So we have this grid, and yeah, straightforward. Just increment the index I. Diagonal, two diagonals. This is a bit more complicated, but let me skip this because I think we understand the idea, right? So in the beginning, in the entrance, we've got the original lines. We know their widths, so maximum column, maximum row, right? It's obvious. And then we can just compute the diagonals. Right, so we collected all those search lines, the lines where we will try to find the words. We create the dictionary. That's good. So to create the dictionary, we yeah, so the comment is much bigger than the actual solution, one-liner. So yeah, just create a hash out of those lines. Probably actually, yeah, we can just after this, put dot set, and the job is done, right? We already create the dictionary, so we don't need all this. Yeah, well, okay, lowercase. But the thing is that here the key is the lowercase version, and the value, yeah, so it's not just set, but probably for our case it's a bit redundant, some extra work. But the thing is that this word in the hash is the original word, probably, like if there are some names, and then it will be capitalized here but lowercase here. So we'll search using the lowercase version, and then when we found this word, we can print its original form. Right, so create the dictionary. Where were we? Create the dictionary, and after that we just search the screen and pass in those parameters, basically the minimum length and dictionary and the search items, the search lines for all those lines. So we loop over the lines. If the line is big enough, yeah, definitely there's no sense to look at the lines which are shorter than the minimum required length of the word to be found in this line. Right, then we search both the line and the flip version, so we don't have to make this where is it, this array twice as big, so we can just get the half, and after that we just flip all those items forwards and backwards. Right, so this is search space, I like the name of the variable, and so begin plus min. No. So yeah, we are just no regular expressions, but just some straightforward looping over those indices, over the possibilities, and making the substring and checking that that string in a dictionary and incrementing the number of found words. Right. I wonder if we collect the result. Oh yeah, definitely. So the found is the hash. Yeah, so it it will contain the number of occurrences for each word there. I don't know if we need that information, but nevertheless it's there. And after that found some different words of length min or more, and the words themselves, right? So print words, and print words is a separate function that gets that hash, where's the found, where the keys are the words and the values are the number of occurrences of those words found in the original grid. I wondered if we can just run the program and see what it prints. Athanasius, Raku, Shahed 2. So in which order we should supply the files? So first it's the grid. Grid is there a grid there? There's no grid there. So first is the grid, and yeah, but we have an example, so it's exactly like in the description. I already forgot where we were. Where I did. Okay, so let's use my Raku reviews 76 grid, and the second argument is dict, is the same Raku reviews 76 dict. Voila. And I forgot the minimum, right? Sorry, like there should be 2 dashes there, right? Minimum, for example, 5 letters. Hey, why? Grid, dict. Yeah, so the order is actually, it's not important. But yeah, so this is what I told you a few weeks ago. So in this case, probably everything was okay. Now file contain the word search, so but all those files exist, right? And this file also exists. But this one, I don't know what happened. I wonder. So this is. I mean, if this condition was not satisfied, then we've got this message, regardless of the correctness of the parameters. But okay, so dash grid. Okay, Raku Athanasius Raku to Raku, dash grid equals the string, dash dict equals the thing dash dash mean equals some number. Well, the only thing that I can think of grid is, but I think I'm making a silly assumption. Dict is like I'm now passing the whole path, the absolute path. No, that was not. Wow, really? So Raku cannot understand this, the relative path, which is a bit strange for me, but nevertheless, okay. So we found 32 different words, and you see, so I passed my original dictionary with a huge dictionary, right? Well, kind of huge, and it found, maybe I want to run it with shorter words and see how quick it gives us a result. How quickly, actually, yeah. Yeah, so, and this is what I wanted to see. So here in this solution, we don't see that, but here in this solution, there are short words which could be found like T a couple of times, right? And like 3 times, and even this word, is it an English word? I don't know what that means. 6 times it was found there in the grid. Okay, that was really interesting thing. Going next, Colin Crain, Raku number 2. Here is the solution. Yeah, but I already see what's there inside. So we start with the files, then the minimum word, the matrix. So we create the matrix out of those files, and we use the cache. Need to cache the internal sequences. The lookup table, basically the dictionary. Copy. So we create a copy. We make it the capital case, uppercase version, and we return this one. So basically this is kind of a set again, so it's not really hash, right? So the hash where all the values are ones. The possibilities for the possibilities is word vectors. Word vectors is, yeah, right. So this is what we determine the dimensions, and we collect all the vectors for all those basically 8 directions, up, down, left, right, and 4 diagonal directions. So yeah, so we just scan the indices and scan them in different direction, and put the characters to the result, right? And then we take those vectors. In what we do, we just, if I'm correctly understand this, we just create words out of those. Well, not words, but just lines for search. Vector words. Yeah. Words push, vector words. Maybe we can just print this. And after that, so we've got all those possibilities, and then just grab those possibilities and check if the no, actually these are the words, right? So these are the words. Lazy evaluation in map sequence above, need the reset to be here. Turn vectors into strings, mid-word letters are longer. Okay, so we reject the short words, right, like here. So this was, I was a bit incorrect, right? So, oh yeah, right. So this is, yeah, this is where the triangle reduction operator can be used. So this is basically with, yeah, so yeah, that's obvious now for me. So we get to this position xy, and from this position we start to go all 8 directions, in all directions, and we collect, like on this example, it's the most, yeah, it's reversed, but still it's an obvious thing. So we just collect the words of different lengths, starting from that point, going to that direction. Right, now I understand. So these are basically the words that we can find at this position, xy. Right, and this is the words. And then we basically repeat that for the whole matrix. So we see the 2 nested loops over rows and over columns. And after that, so here we have all those words, potential. So do we make any uniqueness? No, they are just as they are, and we grab them. And here we go. Okay, let's run this. I want to run this. Raku, Colin Crain, Raku, chat to Raku. We need the word search and the dictionary. Word search txt. I want to see what's there inside. Nothing. So basically, I believe this is the grid, right? The file. So they are the matrix. Okay, so let's take the grid from my location. I believe now I can use relative path because it's Raku reviews 76, because this is shell will process this text. No, not a dictionary, grid. Then I'm using Raku the dictionary reviews 76 dict, and yeah, so we're using dictionary. And we found 33 words of minimum length of 5. Can we change the length? No, it's hard-coded here. Okay, yeah, right. I like this. And virus is even here. Virus. Right. Okay, going next. So it was Colin Crain. Now it's Javier, Raku number 2. Here's the solution. We start with main function, and again the default test case. With the predefined names, we create the matrix, letters to matrix. Where is it? Letters to matrix. So we take the file name as the parameter, and for this parameter we read lines. So we split them by spaces. We push it into the matrix and return that. That's clear. The words dictionary to hash. Again, we get the file name. We pass it as an argument. Possible words. So these are all the words. This is dictionary words, right? Challenge only wants words greater than 5, so just keep those. Right, so we skip everything. We only take the word if its length is bigger than 5. These parentheses are never needed, I believe. Actually, I don't know. I prefer to omit the parentheses, but yeah, that's the basically the test. And this comma can be omitted. We have the comma here, but not here. But that's also right. And actually, in this case, you can also omit the return keyword, right? Right. Okay, so we create the dictionary and the matrix, and we prepare the space for answers. For the answers, so okay, the standard pattern. Again, I really want like that Raku has something that can give you the height of the two-dimensional matrix with a single go without accessing the one of the rows. Right, then we make the full scan. We visit all the characters in the matrix and find words. We do word search, and we push the found items, if there are some found items, to the result, and then we print that. Wow. We take an array, we make a list, we flat that, we sort that, and then we join it with comma and space. And find words. So the main search function here. So it takes the matrix, the dictionary, row, and col. Basically, the row I and j. These are the coordinates, right? Interesting. So we, unlike other solutions, we did not prepare any words. We just go to every solution, to every position, and immediately from that position, after we visit that position, after we visited it, we already know the words that we can find from that position. That's, I believe, a different high level view of the algorithm, right? I also like that it's possible to do it like that. Right, so while, no, wait, that's something non-standard. So we have different directions. So we have 8 directions from 1 to 8. And we compute the next position, basically. So there are like 2 variables, I and j. We either decrement or increment them, depending on the current index in this loop. And basically the index means that we go like up, down, left, right, or diagonal, right? Yeah, and it's fun that it's like nicely laid out. There are 3 in each. Okay, so while those are within the borders, right? The indexes. We take the character and append it to the possible word, which we then append to the found result if this possible word. So basically, we have those words of incremental lengths. One letter word, actually not one, but I believe, right? So there should be 5, right? By the way, do we have a one letter word in this possible word? I believe yes, because I don't see that we do something. Basically, we should then. No. Maybe yes. So H and W, these are the sizes, right? While, so we do while we're within the borders, but what we start with, the current position and we increment the index and we take that index. Right. So yeah, but I believe on line 37 we have to insert the check that this possible word is not didn't achieve actually yet the minimum length, right? Because otherwise we don't have to do. Of course, the dictionary, in the dictionary we don't have those words, so this check will always fail. But I believe we don't have to try to search the word in the dictionary if it's short enough, if the word is shorter than the shortest word in the dictionary. Okay, but that's the small optimization. Probably, actually, we don't know yet which is faster, just to directly go to the dictionary and take a look there, or make some check. Okay. No, we cannot make. So yeah, we have to like insert if. So yeah, if word is in dictionary and the length of the word is less, and first we have to check the length, like here, right? Like not in the line 37, but like here on the selected space. We have to check if the possible word is big enough. Okay, so let's run this solution. Javier Raku 2, and what we need first the letter file and the word file. So I believe I can just copy it from here. So the grid and the dictionary. Yes. And it's done. Again, 33 words. Theorem of virus. Right, so it works. Right, next solution by Loren Rosenfeld. Here it is. Well, I wonder when GitHub will give us the possibility to see the syntax highlighting, the file with syntax highlighting. So the dictionary, the grid file will take it from the arguments of the command line. Then if this argument exists, if the third argument is there, so we assume that this is the length and take this minimum length. The words, we read it from the dictionary file, and we immediately take only those which are bigger than the widths, and we convert it to set immediately. So yeah, this is the true dictionary, right? It's just a list of words, of unique words, actually. Yeah. Then for grid, so we are taking the grid file and creating the matrix in the variable grid. It's a matrix, right? Then we defined again the same thing, the dimensions, but just not the elements, but end. So it's the maximum index for the horizontal and the vertical indexes. Then this is something new, set hash new. So we create the set hash. What is a set hash? It's a combination of set and hash, right? Let's see. Yeah, it's a mutable set. Yeah, so that's the keyword. It's a mutable set. So the set we can change. The next. So there's the function in the middle of everything. So it finds some words in the given row, but we're using this function for different directions. For horizontal, it's a trivial case when the row is basically the horizontal row. Then vertical, we scan it, we loop over the indices, and we saw this somewhere earlier, so we compute the words, and all the rest is just 1, 2, 3, and 4 different diagonals. Right, so here's the find word thing. So we pass. Right, so this find words already gets the rows, which are actually not the rows, but like lines in all different directions, right? And so so there are some strings in which we can find something. And how do we do that? So we scan this, so the index for the length of that line, and we increment we basically put the word into the result, and we do word flipping. Okay, so word flipping is an important thing. Instead of flipping we saw that already. Instead of flipping the source strings, we just can flip the word. But the word is not the word from the dictionary. I mean, we do not loop over the dictionary. We just take the word that is defined by the range of between two indices in the given source line, right? Right. Okay. So this is clear. Raku low rent Raku chat 2. So we need the dictionary. First is the dictionary. Now I have to swap this function, these lines. Okay, so here we are. Looks like it's more or less the same. Going next. The solution by Mohammad Anwar, and we have 2 solutions left after that. Ooh, it's a long thing. It's 1 o'clock in the night, and I have like 1/3 of my battery here. Right. So the main function takes 3 arguments: dictionary, grid, and the minimum size. Words is empty. Anwar always does that trick. I don't know why actually we need to assign the empty thing to the originally created array, but nevertheless, so index puzzles, fetch puzzles from grid of the size. So I believe this is reading the file, right? Right, and it's doing more. So we prepare the horizontal, vertical, and both diagonal lines. Origin and matrix. So okay, horizontal. We take the data. What is the data? Data is the matrix, the grid. Ooh, wow, really? You can do that like that? I've never seen that. Wow, that's cool. I want to note it down and use it later. But you see, so this is a scalar and this is an array. Horizontals, right. But why do we need it? Can I put the at signal here and use it here, and then I don't need this one? Right. So an interesting thing is that the loop variable can make is copy, so we can modify it inside the loop with no side effects on the loop itself. So we remove spaces, we split into characters using the comb. So this L push characters, basically this is the characters, right? And these are the string, the strings which can be formed from these letters, right? Next, unless it's big enough, push. So we flatten this first, then we create. I think this is a bit redundant, but then we put this. Okay, so I didn't see it earlier. Anwar is using this dot before subscription, but also using this dot before accessing the hash element. So when we directly flip the version, right? The current substring. and we return everything. Yeah, we return like 2 variables, unlike all the other things. Where was I? So right, horizontal, then verticals, and so let's see how we. Yeah, basically it's just some description of how we read from the matrix, and we collect those again flipped versions and the direct version into the array, and 2 diagonals. Yeah, basically the difference should be just, and we go into so there are 2 loops in H, right? Basically the difference is basically, I believe, how we do this trick. So here it's minus minus, here it's, yeah. Okay, okay, so we found all those things. See, so it's, yeah, this is, yeah, I wouldn't do it like this. I mean, this is, see the matrix variable, you pass it and you return it, and you pass it again and you return it, and you use it again in the next function. Finally, you save the result here, and it will contain everything. And these functions are not kind of, what's the word, homogeneous, because this one is kind of the same as this verticals, but it returns 2 items instead of 1 for all the other functions. Okay, good. So we've got all the things here in the matrix. So it's not the grid. The matrix here is not the grid. It's just the matrix of list of words, right? In some sense. Here's the dimensions, puzzles, right? So for these source lines, we sort them. We take the pair. I don't know what they're inside. They're inside. We have like 2 things, right? No. This is the horizontal. So inside this we have okay. So the string is the pair keys. Ooh. And this is, we push the word. I wonder where we match the dictionary against the word. Here, right? So fetch puzzles. So these puzzles probably I want to print this, but it will be too big, I believe. Right. Then for those puzzles, then we basically just do the word search, and we append the words if there are some words returned. Why cannot we just return it directly? Word search. The word search is basically our right. So yeah. By the way, interesting thing to notice is that there was a couple of solutions earlier. There was another regex where it was m:(ex:(I). So this adverb can be either inside or outside, right? But if you put it outside, you have to add the m thing before. Otherwise, it, yeah, unlike Perl, you do not put it after the final slash. You put it either inside or, well, in Perl you also can put it inside or outside before the whole regex, so that it's applicable. So that's applied to the whole thing. Okay, so all right, let's run this solution. Raku, Anwar, Mohammad, Anwar, Raku, Ch2. So what's the order? Dictionary. No, again. Woo. Users Ash Raku review 7.6 dict. Right then, this one for the grid, and finally the length is this size. Yes. So the matrix 19 by 16, 170 letters, right? Okay, so some debug information for the slow run program is really a good addition. So just always do that, and probably just processing record. Probably before we process that, probably we can take a look. So we see say print, but actually such things I believe it's better to print to the standard errors instead of standard output. Right, maybe before we get result, grid with space, grid without space. Right, yeah, and also Anwar is always doing the separate test file. Well, not whole, I just said always, but actually it's not always. So there's a test file for the first task, and so basically here's the solution in that you can see in a separate file like .raku, and there are some tests. So yeah, just use test, done testing, and yeah, it's so simple to make additional tests in when you're programming Raku. 13, and yeah, like almost there. Maybe what we can, let's return the solution and maybe we can find. So we see, so there's a debug thing, but it's hard-coded thing. What else we can find here? So we talked about that. I talked about these. So I would probably would either modify it inside a function, just is RW, but actually probably it's a reference to a thing, so we don't need even the RW trait. Right, so yeah, this one is my personal request to Raku, the design of Raku, so that we can get the height of the matrix, two-dimensional at least. These are the placeholder variables, and so we sort these using the values of those items B and A, and you can have like Y and X there, or Z and Y here. It's not important. It's just you sort. It's just the variables which will be assigned in the order of in their alphabetical order. So this function takes two arguments. The first will be assigned to $A. The second will be assigned to $B. Wow, record 27. So I believe, oh my god, so it's not like 17 and 16. So we are going to go up to 107. So definitely I'm not going to do it now. So yeah, I had to stop that unfortunately, but nevertheless. Okay, and we have two solutions left here in this list. So Myoungjin Jeon, yeah, sorry, I cannot read that fluently. Here's the solution. Sorry, I cannot read the solution fluently as well. Okay, so let's quickly do that. So the subset natural numbers, the integers which are bigger than 0. Yeah, I see. So again, the placeholder variable here, you can put star here. Yeah, but you can also use a placeholder or $_. Then there's some class, grid size info, the class, which defines a few methods. Probably will return to these methods. Then there's another class, grid search data. So it was grid size info, grid search data, and finally the main function. So it takes the dictionary, the grid, the flag to print debug informations, right? Information grid. Okay, so we create the grid search data new using the grid. So yeah, grid search data. Okay, this has this file path, original data string, some attributes, get original data. So I believe we should call this, get original data. We call this method first. What it does, it just reads the whole file if this file defined not. If so yeah, this is not a negation, right? This exclamation mark just denotes the private variable, the closed variable, whatever you call it, the variable that you cannot access, the attribute that you cannot access outside the class, and this is the thing that the function will return, the last computed value, right? Then so I will skip debugging. So get all possible words from that grid. Let's look at the function, get all possible words. Okay, this function is using another class and the methods and that its methods. So get string, it's still so it's called in self. You see, so to access the function on the self. There's no like $self, it's just self. And if, yeah, these exclamation marks really look like negation, especially with this syntax highlighting, which I believe is a bit incorrect, right? Because it's a signal. Still, it's the twiggle, but it's a part of the variable name. But when it's read, it's really like not only the exclamation mark means negation, but the color of it also like kind of gives us a hint. But it's not the negation. So okay, so get the string. So if the string is if string defined not. So if there was no string, so what is a string? String is just the attribute, the string attribute called string. So we take the original data, we remove spaces, we find positions of new lines, and this is the line length. If there is no new line, then we just take the length of the string, we remove the new line if it was there, and we convert it to lowercase and then the string. So yeah, basically that's the string from the original something. So get all possible words I was here, right? Then on the grid cipher info object, we call this all subsequences indices, and we then convert the result. Basically, we join the characters together, right? We take unique things and we sort them. Okay, so this is what I want. All indices. I wanted to find. Yeah, I found this. So it take all indices in both directions. It maps those. So many flattening. Yeah. So all indices, what is it? It's all indices in both directions. It's a Boolean flag, right? And by the way, notice when you want just to set the flag to true, just pass its name to the function. You don't have to set like =1 or =true. Just pass the name and it means that it's defined. So the direction call with, what is it? Call with dispatch. Calls the next candidate match. Yeah. So you see, so this is the multi-method, and there are different multi-methods with the same name, and we can dispatch that, and we can so calls the next candidate matching the original signature. That is the next function that could possibly be used with the arguments provided by the user and returns. So yeah, if there are more than one function that satisfies basically the signature that it gets, the capture, then we can call a different thing here. But why? Both direction or direction list return. Right. So yeah, I think I will not understand that how it works, but maybe we can just run that and just look at the things of the Raku syntax. Right. So let's Raku Jeon Raku Ch2. So what we need? Where's the main function? The main function is here. So what we need the dictionary and the grid, obviously. And that's it. So we cannot set the size, length. So that's the grid. I hope we're not going to print the dictionary. Right, so words found, but I want to see the words, right? So this is the matrix, I believe, and these are the words that were found there. But I believe this is not 534 words, right? And where are all those viruses? A theorem, I see it here, and spasm. Yeah, kind of this one, but probably somewhere else as well. And there was rape, I remember, and USSR. Okay, nice. So there are two classes used there. And finally, the last solution in this list today, Roger Bell West with the solution for the crossword thingy. So what we have here, so the minimum length is hard-coded from the, as the task required, 5 characters, the minimum word length. Then so we take the file, the puzzle file, we scan the lines here, we globally, so we see, so in Raku you can either use just G, colon G, or column global. So there are 2 options for you, just the short word and the word, the long version of the adverb. And I don't understand why we need that. So it's chomp, it's I think it's a Perl pattern. Right, nevertheless, so we make it a low-case version of the thing. So remember that we are using the grid. If defined y, what is y? So it's the variable which so for the first time we do it like this, the number of characters in this line. Otherwise, if it's different line, okay, so not rectangular. So this is how we define that the puzzle, the grid is not correctly set. Then, okay, so we push to such spaces the line, the horizontal forward from left to right, and push to the grid the letters from that line, and we push the reversed line, the horizontal line from right to left. Good. Then, okay, then I already understand what happens next. Then we do scan something vertically and push the flipped and direct version of the vertical line there. Right? Then obviously diagonals. So yeah, so here is this, like we match that we are within the borders, and again we push the word in its reversed form, the line and the reversed line. After that we are reading the dictionary from the first argument. We scan the dictionary and okay, so again, so we are reading the dictionary, and for each word in the dictionary we try to determine if this word exists in those lines. If characters, if there are enough characters in the word in the dictionary, we do this trick. Otherwise we just skip that word, we make it lowercase, and for all the search spaces, so yeah, the complexity of this algorithm, I think it's quite high. We scan that, and if this index or width does 2 things, if you remember from the previous reviews. It first, it will topicalize the thing if it exists, and it will execute this block if this is defined. So if there is the word from the dictionary found in the search spaces, then we can print this. Okay, so I believe, I wonder if there are some files. There are no files there. So we can run this function against the dictionary. So Raku, Roger Bell West, Raku, chat 2, Perl 6. So we need to pass 2 things. So the first argument is the path to, so here I can use this one, right? Because this is shell. Raku reviews 76 grid, the puzzle. I believe it's fine because it will remove spaces. My file contains spaces. Then we need dictionary 076 and dictionary, but definitely I don't want to supply the whole dictionary. Let's just skip. Well, maybe maybe just make Perl Weekly. Hey, it's still Perl Weekly Challenge, Mohammed. His solution challenge 76. Mohammed Raku. What was there? Shahed 2. No, it was not. Who was that? What's Markus Holzer, I believe, right? Markus Holzer, Raku, Ch2, like words, right. Okay, yeah, and there are some words found. Okay, that was it. That was the last solution in our today's list of Raku solutions of the second task of the week 76 of the weekly challenge. We were looking at the grid of characters and trying to find the words in all different directions. And yeah, so yeah, it was another long review, but still I hope you found some really useful information about the Raku programming language there. So yeah, hope to see you next week. Stay tuned. Success.